GM, and happy first ever Arbitrum Day. So today I'm going to talk about Stylus. We're going to go over what it's about, its advantages, all sorts of fun stuff. So, okay, today we're going to talk about a technology that's going to onboard millions of developers, that's over 10 times faster than traditional methods, that opens up several new crypto use cases never before seen on Ethereum, and that's coming out this year. So, very soon. If we want to get to a million developers, or why would we care about that? Well, you'll often hear teams talk about like, how do we get to the next billion users? How do we scale to where, so much of humanity is using cryptocurrency? It's useful to take a second to look at where we are and to recognize the opportunities before us. Right now, those studies seem to vary a little bit. There are at most about 20,000 Solidity developers who use Web3. So these are about, just a few thousand, maybe a couple tens of thousands of devs who know how to write smart contracts, know what Solidity is, and, could deploy something. And that's really awesome. So much has been done with that 20K. It's truly remarkable how big this industry has gotten off of that small of a user base compared to more traditional technologies. So by comparison, while there are thousands of Solidity devs, there are about 3 million Rust developers and about 12 million C++ devs. Indeed, when we look at the programming languages that Web2 uses, there's just orders of magnitude more. And if the goal is to scale to the next billion users, we're going to need to scale to the next million devs. We need to onboard more people so that we can build the technologies of the future. So, to address this problem, different chains present different solutions. We have the traditional EVM world, the Ethereum-like chain. So this would be like Ethereum or, of course, Arbitrum 1 or any of the other so-called EVM-compatible or EVM equivalent L2s and all L1s that one might look at. And they're amazing. They let you do all of the stuff that has already been written in Solidity and what have you. And then there's other chains. I give two examples here, but there's several that might say, instead of Solidity, let's try and go after those other developers. So we might on Solana do Rust, or on Near you might do Rust and C. Different. If you have a programming language in mind, there is a cryptocurrency platform with it. The only problem is it's a divided world. It's a world where if I want to use new programming languages like Rust, I have to do them on a chain that doesn't have all of the popular dApps that the Solidity world has created. So many people have tried to replicate all those wonderful DEXs and NFTs and applications that we see in the wider Ethereum ecosystem, but it's just very, very challenging. So a very natural question emerges, which is, can we have them all? Is it possible to have all those new programming languages and all those new ways of doing things while simultaneously having all the existing stuff? That's exactly what this talk is about, and that this technology seeks to address. So Stylus is a next-gen programming environment for Arbitrum chains that's coming out this year. And just super high level, what it essentially lets you do is deploy smart contracts written in Rust, C, C++, and more. We'll get into how it works, but just looking at it from a high-level bird's-eye perspective, essentially the idea is, in the same way one would write a smart contract in Solidity, have all of this on Arbitrum chain, so it's not split over many. So when we talk about having multiple programming languages, we're talking about having these all be super deeply integrated together. And in the Stylus model, it's all fully composable in the sense that if you're working in Solidity, you can, call a Rust program. You might be able to, go rely on some dependency that's in another language. But similarly, if you're working in C and you wanted to go deploy something written in that language, you're able to access all of the Solidity goodness that exists on Arbitrum 1 and Arbitrum Nova today. So yeah, I definitely really want to stress that there's so many advantages to having access to all of that liquidity and ecosystem and the users and all of that are currently on Arbitrum today without having to like work on some other network that you then have to bridge over or what have you. This stuff is all working together. And we'll explain how this is possible in a more technical sense soon. But just a couple of things I wanted to clarify though before moving on. When we say that Arbitrum Stylus is coming out, this is not a new rollup. This is not like, some new L2 or what have you. It's an upgrade to existing ones, and it's also the ability for these orbit chains, which we'll have a talk about later, to use new programming languages as well. So every Arbitrum chain that you see today, every Arbitrum chain that will be deployed in the future, will be able to use Stylus to achieve these ends. And when I talk about there being several programming languages, I don't want to make it sound like that Solidity is necessarily bad or that we aren't supporting it in full. In the Stylus model, it is exactly as before. Any contract you have deployed on L1, if it works on Arbitrum today, it will continue to work on Arbitrum tomorrow. And that's pretty much everything given how equivalent Arbitrum is as a technology. So let's jump into how that works, which will help clarify the exact parameters here. So how we have built Stylus is by thinking a bit out of the box here. You see, a lot of times people will ask like, oh, so do you take Rust and turn it into Solidity? Or do you take these programming languages and, somehow make it EVM bytecode? Like, how does this work? Well, it turns out the solution is to actually have two virtual machines. So we have the Ethereum virtual machine. So if you're writing a Solidity program or a Viper contract or what have you, you can deploy these to Arbitrum and it'll behave exactly as before because it's using the exact same EVM. It's the same technology. But if you're working in Rust or C++ or C, you can compile these to WebAssembly, also called WASM, and run them that way. So we've got two VMs that work together. A little bit on WASM. So most modern compilers, the kinds of language, the tools that languages use to produce machine code you can actually execute, are able to create WebAssembly. And what WebAssembly is a web standard, hence WebAssembly, that browsers like Firefox or Google Chrome or Brave are using to speed up computation. So, a lot of code is written in JavaScript on the web, and there's some other languages and all these great frameworks. But if you want things to be like super performant and you want to do like, really cool GPU stuff or what have you, WebAssembly exists for these purposes. And it's lightning fast, and we have found a way to bring it to the blockchain and deploy it on L2. So it's two composable VMs. But the cool thing is, from the user's perspective, that doesn't matter. Everything just works. So it's not like you have your Rust ecosystem and you have your Solidity ecosystem and you have your other language ecosystem. They just all work together. A contract in one language can call another, and there's absolutely no difference. You never have to care about the specific implementation details of another, and it's because it's all got the Solidity AVI under the hood. So you can have an ERC20 trading on your favorite DEX written in Rust. It's one state transition. So what does that mean? Well, the fundamental unit of change on a EVM chain, or on Arbitrum specifically too, is the transaction. So a transaction makes some kind of modification to the state, and if it doesn't revert, is committed permanently to the blockchain's ledger. And basically how this works is the two VMs just work together to affect a state transition. So if during the course of an aggregation call or something, right, that someone's doing, a Rust program is invoked, or a C or whatever. When I say Rust, I'm really talking about any of these WASM languages. Then that part of the result will be done in that virtual machine. But if that Rust program, say, were to then call into an EVM smart contract, so something written in Solidity, well, then that part of the result will be computed by that VM. And this is what we mean by they're composable, like they work together. It's one database, so it's like, one node software, one implementation, and one state trie. And what we mean by that is all the contracts, all of the state storage, it's just like in Arbitrum today. So if I'm in Rust and I decide to save something at a specific address, at a specific slot, I can do sload and store just as I do in Solidity. And it all just works because under the hood, though there are two ways of computing results, They both commit results the same way. They both access the same data structures and storage. And lastly, there's nothing like this. So you might hear on other platforms, particularly all L1s, they might say that, oh, we also support Solidity. So you might see like there's a compiler that might, take Solidity code and turn it into like Berkeley Packet Filter or into WASM or one of these technologies that are used in the alt world. Well, the problem is that that's kind of like second-class support for Solidity. And if you've actually gone and tried to develop on these platforms, it just doesn't feel right because, well, it's like Solidity, but it's like shoehorned to be WASM or whatever these other techs, whatever tech they're using. And so there's just all these limitations. You like look at their documentation, they say, oh, addresses are a different size and these structures and patterns that you're used to, you can't use. And, oh, you have to go do this very weird Solana-esque thing or something. So when we talk about having two VMs, this opens up the advantage of both of these are first-class citizens. Like the EVM contracts, the WASM contracts, they're all treated exactly the same way. Okay, so this actually has some very great implications. One is that Stylus is way faster. So a program written in C, C++, or Rust on Arbitrum will be substantially cheaper and faster if it's like a high compute type thing. So as an example, I took Ketchak. This is a common hashing algorithm used in, kind of everywhere in Ethereum. And looking at a pure Solidity implementation and a pure Rust implementation, we were able to find that, like, if you're just looking at the time it takes to complete a call, doing that Ketchak process is 73 times faster in Stylus. So, right, that Rust implementation is performing so much better and therefore is so much cheaper. And to explain kind of some of the intuition for that, WASM has a faster runtime than the Ethereum virtual machine. And this kind of makes sense, right? Like Google, Apple, Microsoft, all of these companies want their web browsers and want their other server-side applications to be really, really fast. And, well, in order to do that, they've put in so much work optimizing and JITting and doing all these things that make running WASM code on your web browser super duper efficient. And we now get to take advantage of that on Arbitrum chains. The other thing, too, is the compilers for Rust and C and C++ and other languages just generally produce more efficient code. And this is because they're getting to take advantage of things like LLVM or GCC, these, decades-old projects that are the culmination of all of this research and all of these breakthroughs, whether it's in the corporate world or academia or just, open source developers. Everybody's been working towards making a language like C, say, super efficient. And so you now get that efficiency, you get that superior bytecode on in this model. But you still get all that Solidity stuff too. So there's no downside to adding this on top. And this enables some very interesting new use cases. Since we're talking about computation being so cheap in the Stylus world, something like cryptography becomes possible in a way that's currently infeasible on most EVM chains. So, if you're working on a mobile wallet and you want to use the secure enclave, to make that user experience better, to get more people using crypto, lowering that barrier to entry, having that nice wallet means using the cryptography that phone uses. And if you look at, say, an iPhone, you'll see that the secure enclave uses a curve called P256, also called SECP 256R1. You don't need to know what all that stands for, but the good thing is this. There's a specific piece of math that needs to happen in that phone in order for it to be secure and supported. And right now, the EVM just doesn't provide this. So if you try to go implement that in Solidity, it's really expensive, it's challenging, you have to make your own implementation and audit it. And generally, we find that for a lot of cryptography, it can cost millions of gas. But in the Stylus model, you can take your cryptography as is. You can go take that standard reference implementation and, in most cases without modification, just go deploy it to Arbitrum 1. And so any Stylus-enabled chain then is able to iterate really quickly on these cutting-edge technologies. If you've got some new bridge that you want to make or some new ZK circuit verifier, you don't have to wait on L1 or on Arbitrum to hard fork in support for the things you want. If you can think of it, if you can write it, if you can go find a standard library for it or an implementation, you can just deploy that very quickly and get efficiency. And that opens up use cases too in gaming and AI. So these are high compute. Let me touch on gaming for a second. A lot of gaming is written in C++, and when we talk about scaling to the next billion users, we're talking about lowering the barrier to entry, right? Right now, if you're working at one of these traditional firms, well, you'd have to explain we need to hire a Solidity engineer or, go learn it yourself. And there's just all of this upstart time necessary to get there. This is challenging. And so to make things a bit easier, in the Stylus world, you're able to take C++ code and with, way less of a learning cost, just go, take your C++ code and deploy it to the blockchain. So this is great for that. And in terms of AI algorithms tend to be very computationally intensive. And so these kinds of use cases become possible. Lastly, you may see that oftentimes for layer 1 Ethereum or for Arbitrum, people propose, hey, what if we added some new kind of, what if we added some new precompile, some new thing that the EVM does really quickly? Well, I think what's really exciting about Stylus is that now those people are able to go iterate on their designs on a live network. You don't need to fork Ethereum and test some sidechain or, work with some testnet that, requires knowing all of this DevOps and knowing all of these things. Instead, you can just go take that super duper curve that you wanted to load or whatever it is and deploy that to Arbitrum stacks. And then suddenly you can work with that, iterate on it, and it'll figure out all of the gas stuff and everything for you. So I find this to be a really cool way that Arbitrum is going to be able to be involved in, some of the research efforts in Ethereum because, we're scaling Ethereum together. Okay, now I've talked about a lot of the advantages. Let's get even deeper on how it specifically works. A very common question is well, how does gas work, right? In the Solidity world, every opcode has a gas cost. And if I were to go do an add instruction, say, I might pay 3 gas to do that. If I do some other instruction like store or whatever, I might pay thousands of gas. And, before every instruction runs, you pay some amount of gas and you get a receipt back after your transaction. Well, we actually have a really efficient way of doing gas, and that ensures the safety of this system. So how it works is this. If we're looking at the example Rust program here, we first split the program up into what are called basic blocks. This is compiler terminology, but the only thing you really need to know here is that in a basic block, we say that it's unconditional, that there's no jumping. So you'll notice here, these first 2 instructions, they don't go anywhere. They just compute something. But then once we get to the if statement, depending on the value of this, we might go here or we might go here. So in practice, this would be WASM, but we're looking at Rust together and what it would compile down into. So you have some kind of operations and then a jump. Okay, well, at the top of each of these, we introduce some gas metering. So how that works is at the top of the block, we check for how much gas remains. And if you've got enough, no problem. We deduct a little bit of gas and then you run your computation. Otherwise, we trap. And by trap, I mean the VM suspends, the transaction reverts, and you're out of gas, which is sad, but that's what happens. So you pay before each block. Well, this is actually super cool because it's incredibly efficient. In the EVM model, every single opcode costs gas. So to do an add instruction, I run an add and then I pay gas. The next instruction might be to go take the result of that and store it somewhere so that I pay that amount of gas to go store it somewhere. In this model, we do entire spans of computation before ever having to charge gas. Once you've paid for the one up here, you get to have all of this stuff, all of that gas metering for free until you get to the next block. And in practice, this turns out to be way more efficient. So it's way more efficient. And then one last thought on that. Something that's really cool about, and where this happens is after you've uploaded your WASM to the chain, there's a compilation step that happens on everybody's nodes and their validators that turns it into this form. So you upload an untrusted WASM, something that could be crazy malicious and do anything that's bad. And then we apply these instrumentation passes that we're talking about to transform it into a format that's safe. So once you've done this, you don't ever have to worry about an infinite loop, right? Because a loop will always consume gas. The code in it will always have some kind of trap if you run out. And then, that loop that was malicious originally in your code is now suddenly able to be priced out and suspended. Okay, now we keep talking about WASM and how this makes that possible. Why not use a rival architecture? Why not use, as say Optimism does, MIPS, or as some of the ZK teams might use RISC? These other architectures are a bit different. In the WASM model, everything is structured. And what that means is we're able to perform static analysis. That is, we can analyze a program and learn tons about it before ever having to execute it. You're able to know things like how deep is the stack, and is it possible for this specific slot in memory to be accessed? And when you have that, you get something called sandboxing. I want to remind y'all that this is a browser technology, right? This is the most adversarial environment that code has to be ran in, right? A web browser, you go on a web page and something totally untrusted executes, and you got to make sure that you're able to not get, hacked or have some kind of problem. And we're basically taking advantage of that exact, the exact same tools that web browsers use. So we're able to look at user code, and instead of trying to do stuff at runtime that's really expensive to protect the chain and that might be, very error prone, we're able to eliminate entire classes of malice right from the get-go, so that in a single cost to compilation, you can forever forward trust that this program is not going to do something nefarious. And the other thing is just that, because it's WASM, it's got all of this awesome tooling and all of this industry support from Google and Microsoft and Apple, like we were talking about, and all those other tech companies. So there's great runtimes. The industry is amazing. The libraries are fantastic. And so, we're really getting to take advantage of a maturity that you might not find in another ISA, as they're called. So that's a little bit of insight into why we did that. And one last bit, the creator of Docker, or one of the founders of it, the primary one, Solomon Hykes, he actually said that if it weren't for the fact that WASM didn't come out earlier, they wouldn't have had to make Docker. So if WASM existed in 2008, as he's saying here, along with the standard library called WASI, which we might talk about later, you're able to do all of this virtualization, all of the sandboxing, all of the safety stuff, the things you might care about in Docker. And that's quite the endorsement for the technology that he would say that. And what's really cool is the Nitro tech stack, that big upgrade we did that Arbitrum had last year, was basically just a bet on the WASM future, right? So we use all of our fraud proofs are in WASM, and Stylus is the natural extension of that. We've got fraud proofs in WASM. Why not execute WASM? Okay, just other examples of instrumentation we do. There's a bunch more for other resources, but I thought it might be informative. So one thing you got to be careful about is not running out of stack. Different computers can run out of stack in different ways. This is the so-called stack overflow. And the way we mitigate this kind of thing is by splitting up a program into its functions, and then at the beginning of every function, deduct a little bit of virtual space left. And then, if you're out of space, that is, if you've used too much stack, we trap. Otherwise, you run your function, and then at the very end, you give back that space. Unlike gas, you get stack space back, right? If you return from a frame and that pops, well, new frames can come in its place. Okay, let's talk a little bit about fraud proofs. So I'm really proud to say that the Stylus, right now, Stylus has complete working fraud proofs. These aren't MVP fraud proofs. This isn't theory, they're complete. And I wanted to just explain a little bit about how they work. We'll have a longer talk about the challenge protocol and how fraud proofs and stuff are done. But I just thought I would go through a little example to show you kind of the differences that Stylus presents and how it just is a natural extension of the WASM technologies that we've already built. So right now, if you read this diagram from left to right, the way this works, okay, got the laser pointer. So the way this works is you read this from left to right. And right now, when you do a fraud proof, there's a so-called execution history that begins at time equals 0. You'll learn more about that later. And then ends at some commitment to the state. So over the course of this execution run, things happen. Transactions are executed, sequencer messages are processed, all of that good stuff. Well, right now it's pretty simple. Everything happens inside the so-called Nitro stack, which has Go Ethereum and has various compression systems and things of this nature. And if one wants to determine that fraud happened on the chain, that is that, that when someone who's withdrawing tries to lie about the state of Arbitrum, you will essentially bisect this history down into a specific step that you disagree on and then challenge that step. Well, here's the changes that the Stylus model makes to that. One thing is, now that we can actually instrument WASMs and do that gas stuff that you saw, we're able to actually fraud proof them directly. So right now, if you want to fraud prove an Ethereum transaction, what you really do is fraud prove the Nitro source code over Ethereum. If you want to right now fraud prove an Ethereum transaction, what you do is essentially prove fraud. You execute and bisect over a history that includes how Geth handles that transaction. But what's really cool is we can actually, instead of just using Geth, we can take these untrusted WASMs, these potentially very malicious programs, and just throw them in the path. So what might happen at the beginning is some Nitro code is running and some transactions come in and they do a bunch of EVM work, but then all of a sudden somebody calls into a Rust program. And that will then cause us to jump from Nitro to that user program in our fraud-proof history. So we run through that user program, and then maybe that user program calls another one. And so then now we're here. And then eventually we might exit both of those and be back in the stack. And then, maybe that same user program comes back again. And that could be an example of a execution flow. Well, what's really cool here is we actually now know certain properties about these so-called user programs. One of them is that they can't go forever, right? Because of gas metering, if this is just the sequence of events that occur, well, they can't be unbounded because you pay for gas, right? And because gas is done at every basic block, this thing can't just go on and on. Similarly, so that means that, this will eventually halt. If I were to just continue using gas forever and ever and ever, eventually I'll stop and we'll go back to Nitro, which will clean up the fact that you reverted. We'll go into more details on fraud proofs to make this make a bit more sense. But another thing too is if something that was like really bad happens, like say a panic or, it tries to do something bad, well, we can actually just halt, or it never gets into this case where as the chain was running, you hit like a true halt where the thing has to stop. And that's because due to the instrumentation and the runtime stuff, we're able to just suspend execution the moment something bad happens and jump back. Okay. And it's exactly as before. You bisect over the history down to a specific instruction you disagree on. And it's just in this case, that instruction might be inside a WASM. So right now it would be inside the EVM, but now it's able to be inside a particular user program. So if two validators were to bisect over this and finally reach this instruction, it might be a division. They just perform the one-step proof that's standard in the Arbitrum system on that instruction. And if there's an error, we gracefully handle it. So like suppose that instruction did a division by 0. Well, instead of the whole chain halting, that program halts. And, you might fraud proof the fact that that happened. Recall, WASM is sandboxed. We have security here. Okay, so that's fraud proofs. So leaving some of the technical stuff now. Where are we? Well, in terms of our progress, we have a completed working fraud prover. So, that's right. So this is not just some theoretical talk about a technology that's coming out 5 years from now and a bunch of promises that never get completed. This is like a real thing. And the fraud provers are complete. So what comes next? Well, we're going to release the full thing this year. So we're going to propose to the Arbitrum DAO this model, and we're going to have this on orbit chains and all of that. And it'll just become a technology that everyone's able to use and that the DAO is able to consider. The other thing is we're going to have a testnet very soon. So by the end of this year, we will have Stylus. Well, before that, we want y'all to be able to actually test it and use it and, port your dApps over, give it a shot. I think you'll find the systems really, really pretty and fun to use. So we're going to give y'all that very soon. And this stuff will be coming out this year. That's basically it. So that's Stylus.